Okay, after this theoretical part, I'm going to talk about the implementation of the Goertzel's algorithm. Okay, I need two equations for that. First, I have a recursion Sn is equal to xn plus 2 cosine omega c Sn minus 1 minus S of n minus 2. And I have a second equation which is based on the FIR filter that we defined earlier, which is yn is equal to Sn minus e to the minus j omega c Sn minus 1. Okay, so we compute equation star for n is equal to 0, 1, all the way up to capital N. Okay, and we assume that S of minus 1 and S of minus 2 are equal to 0. We compute Sn up to n from 0, 1, all the way up to n, capital N. And in the last stage, we compute y of n as S of n minus e to the minus j omega c S of n minus 1. And that's it. See, we don't compute this yn for n is equal to 0, 1, 2, all the way up to capital N. We computed it only once. Only once. Then we know from the theoretical analysis that yn is equal to x of e to the j omega c times x of e to the j omega c times e to the j omega c. And this is summation n from 0 to capital N xn e to the minus j omega c times e to the j omega c. Okay, so if you wish to calculate the magnitude of the dTFT, we simply compute the magnitude of yn. See, the magnitude of e to the j omega c is simply 1. Or if you want x of e to the j omega c, then you multiply yn by e to the minus j omega c, and that's it. Now, this is computationally more efficient than straightforward computation of x of e to the j omega c, because to compute a single Sn, we perform a single real multiplication. So we perform capital N real multiplications here, and in the last stage we have a complex multiplication and another complex multiplication here for x of e to the j omega c. Now, if you want to compute x of e to the j omega in a straightforward manner using the definition of dTFT, you have to perform capital N plus 1 complex multiplications, actually capital N complex multiplications, and for the n is equal to 0 case. Okay, I forgot this little n here. For for n is equal to 0 case, you don't need to perform any multiplications, but complex multiplications are more expensive than a real multiplication, obviously, and as a result, this Goertzel's algorithm is computationally more efficient than straightforward implementation of DTFT. Now, it's also faster than FFT if you want only a specific frequency in the Fourier domain, because FFT is n log n type algorithm for n is equal n power of 2, but it computes all the coefficients, all the DFT coefficients. Here you compute a single frequency. Another advantage of Goertzel's algorithm is that you compute x of omega c with a specific, with an arbitrary omega c. It doesn't have to be 2 pi k over capital N. Okay? And this concludes the second part of Goertzel's algorithm.